Now, drawing the unit circle, that's an illustration of some relationships. So it's not necessarily an efficient way. It's not a very quick way to get our inputs and outputs that are exact. They're the exact irrational output. But the more one draws that unit circle, the more familiar one becomes with the patterns. So what one might want to do on a final exam is be able to do this. Okay, let's say we're needing an output for tangent, because we're going to need to know that the tangent of pi over 4 is 1. So I generally list my 5 common angles and radians across top, and then I train myself to list the 6 trig functions in the same order every time. So I train myself to write 0, then the smallest common reference angle, pi over 6, pi over 4, pi over 3, and pi over 2. If you take those angles I just wrote, any of them, if you multiply by 180 over pi, you would get to degrees. But I really kind of want us to bypass that. I want us to memorize 0, 30 degrees, 45 degrees, 60 degrees, 90. 0, 30, 45, 60, 90 in radians. And notice this convenient conversion factor is a convenient version of 1. 180 degrees is equivalent to pi radians. Half a rotation is equivalent to pi cosine of theta first. If I can remember, cosine is even and starts at her maximum 1. And then you write down the outputs 1, square root 3 over 2, square root 2 over 2, decreasing to 1/2, decreasing to 0. We can illustrate those facts with the circle, but if you memorize that line, you'll be able to fill in the other 5 lines almost for free. Okay, so if that's a challenge for you right now, put a big star by it. If it's a challenge to go from unit circle to this first line, that's a point where you can exercise and get that fixed, and it'll save you time. Cosine and sine are co-functions. So complementary angles have the same output. Quick and dirty, you can just start here at pi over 2 and follow the same pattern. Put 1, square root 3 over 2, square root 2 over 2. And then if you look back at it, if we were to graph sine, sine would be odd, and so it would have to go through the origin 0, 0. Now, if you're in radians on your calculator, okay, hey, good morning, Zoomers. Are you hearing us now? Like for the last 2 minutes, I hope. Yeah. Okay. Okay. So I'm seeing some old chat notes before I hit audio, I guess, and so I just want to make sure. Good. Happy Thursday. Okay. So you write down cosines. Output is 1 at 0. You decrease down to 0 in the first quadrant. Just turn around, write the pattern again backwards. So to get, this is where we were headed. We need to know the tangent of pi over 4. Zoomers, I told the face-to-facers we're going to use this tangent line to graph. how do I go from the first two outputs, lines of outputs, to the outputs for tangent? Yes. This is one of our quotient identities. Take the output of sine of theta, divide it by cosine of theta, and typically we reduce. So you go right above to sine, get the numerator, then above that to get the denominator. Tangent of 0 is 0. Tangent of 0 radians is the ratio 0, which is unitless. Tangent of pi over 6 is 1/2 divided by square root 3 over 2. You can cancel a factor of 1/2 top and bottom. So 1 over 2 divided by square root 3 over 2 will reduce to 1 over square root of 3. Cancel out the 2's. Okay. What is the tangent of pi over 4? 1, yeah. So no calculations needed. Something over itself is going to be 1. Tangent of pi over 3 is this fraction over 1/2. And then the tangent of pi over 2, we try to do 1 divided by 0. But we recognize that's undefined. Okay. Cosine along its vertical asymptote. Similar to sine, tangent is increasing on the first quadrant. And it blows up. It goes unbounded as theta approaches pi over 2 from the left. Zero maps to 0, origin. Pi over 6 maps to this decimal. Caleb, have you found that decimal by any chance? Okay. Let's put that. Wait. And then the reciprocal. 5800s would be 158s. It's almost 2. What is square root 3? Caleb, if you don't mind. I don't care if you know those decimals or not. I want you to know that tangent is increasing, starting at 0, as we move right towards its vertical asymptote. I think it's most helpful next to memorize that tangent is odd, not silly or weird. Whatever positive order pair it has, you reflect that twice, it's going to become a mirror image. It's like rotating going around. So this ordered pair, pi over 4, 1, has a rotational image at negative pi over 4, negative 1. Oh, I didn't put that. I'm kind of getting beyond my good drawing. Half of the tangent function is concave upward from 0. The other half is supposed to be a rotational image, concave downward. And I should have it squeaking up here. Would it be helpful to summarize the steps of graphing the first cycle? Just talk about attributes of this graph. I'll do attributes here it is. Yeah, that's where it goes. Okay, so put these two together. The tangent is always increasing on its domain. Always increasing. But it's going to have discontinuities at the odd multiples of pi over 2. So it's going to have vertical asymptotes at negative 3 pi over 2, negative 1 pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so on. Attribute, 2 of them. Tangent's always increasing. When you draw it, your arm will always go upward, unless you just jump over a vertical asymptote, then you can pick up your pencil. Attribute 2. Places where you pick up your pencil for the basic function is always multiple of pi over 2. Odd multiple of pi over 2. Where it's undefined. Question. Why is tangent theta undefined at theta equals pi over 2? And let's just go a little further. You got it. Originally it's undefined, and tangent of theta can be thought of as, yeah, but why? Because you can also think of it as sine over cosine, and cosine of pi over 2 is 0. Your answer is right. We would be trying to get 1 over 0, which is undefined. But I want you to go a little bit deeper, because tangent is evaluated as sine over cosine. Is that concern on your face or confusion? That's great. I'm an advocate. Oh, okay. So attributes, and then what's the behavior here? When we jump over pi over 2, our next intercept is going to be pi units from 0, and then I'm going to increase up to that intercept and increase again until I get to 3 pi over 2. For every interval length pi, we'll get 1 cycle of tangent. So between 2 asymptotes, we can draw an entire cycle of tangent. And it goes from being unbounded below, heading the axis midway, to